Hey everybody, in this video we're going to be doing part 2 of this section. So last time we talked about graphs of equations and two variables and the intercepts of the graphs. This time we're going to be talking about symmetry. So we had some objectives and we did the first 3, so now we're going to be testing an equation for symmetry. And then there's 3 ways that we're going to look at that, so 3 types of symmetry with respect to the x-axis, y-axis, and the origin. And then note how to graph key equations. Okay, so we're going to test an equation for symmetry first with respect to the x-axis. So with respect to the x-axis, think about this symmetry. Think of the x-axis as like a mirror. So if you were to place a mirror here across this x-axis, all the way across here, and you could flip over your graph and get the same image, that's symmetry with respect specifically to the x-axis. So every point on your graph, like let's say this one here is x comma y, if you were to flip it over vertically across the x-axis, x didn't change. Notice you still have the same x number right here, but what did change is your y value is now negative. Okay, so it flipped over the x-axis, and so what was right here, which was some positive y, is now down here as negative y. And so any point on the original graph is going to have an x comma negative y on the symmetric graph. So here's an example. So if a graph is symmetric with respect to the x-axis, if 5 comma 3, which is right here, is on the original graph, then the symmetric point across the x-axis is 5 negative 3. So it just mirrors down across the x-axis. Now with respect to the y-axis symmetry, think of the mirror as being right here on the y-axis. And so you have the same image on the left as you do on the right. And so any point that was on the original graph, like let's say this one here, x comma y, the symmetric point across the y-axis would be negative x comma y. So this time, what didn't change was the y value. Notice you're still right here at the same y coordinate, but what did change was your x. So what used to be x right here, like positive x, when you flip it over the y-axis, this is now negative. So this is negative x. Okay, so in this example here, notice our point is going to move across the y-axis. Uh-oh, there's actually an error on this one. Cross this one out, and we need to move a little further. Negative 5, 3. So let me color that in black. That one should be right here. So we have this point that's exactly mirrored across the y-axis. Negative 5, 3 and 5, 3 are symmetric across the y-axis. So then our last type of symmetry is with respect to the origin. So this one is a little different to think about. It's not quite like a mirror. In this case, the origin is your point of symmetry. And so there's sort of 2 ways to think about this. One is to think of it as like the point traveling through the origin to its symmetric point, or maybe like a rotation. So if my original point is here, x comma y, then my symmetric point with respect to the origin, you can think of it like my first way that I mentioned. Let me change colors here. I said think of it as like going through the origin to the other point. Okay, so that would be negative x comma negative y, or you can think of it as like a rotation if that helps. So your other way is like saying, okay, I rotated around, my whole graph flipped over there. So like this point here, flipped over there, rotated around there. But if that's confusing, then just think of like I did the first time, going through the origin. So let's highlight the other points so you can see what I'm talking about. Like this point right here, if I go right through the origin, then there's the symmetric point, same distance away from the origin. Same thing here, this point, go through the origin, and there's that symmetric point. So if you have symmetry about the origin, then your original x and y, then the symmetric point is negative x and negative y. Okay, so take a look at this one here. We're traveling through the origin. So the point that was 5, 3, the symmetric point with respect to the origin is now negative 5, negative 3. Okay, so we have our tests for symmetry. Now let me explain why we do this, and that hopefully will give you some more meaning to it and then help you remember these tests. So if you have an equation of a graph, like let's say you don't see the graph. If you saw the graph, you could tell by looking if it has any symmetry. But let's say you just have the equation and you are asked to graph the equation. Then if you know that there's some type of symmetry, whether it's with respect to the x-axis, the y-axis, or the origin, and sometimes it's all three, by the way, then you can graph it much quicker than if you didn't know. So if you know there's, for example, symmetry about the x-axis, you can plot half the points and then just mirror them across the x-axis to get the second half of the graph. So it saves you time with graphing if you do this test. So these testing for symmetry. So there's three separate tests. So the one for the x-axis is when you have your equation, plug in a negative y into your equation and then simplify. If you simplify and you get the same as the original equation, so it's equivalent to what you started with, then there is symmetry across the x-axis. Similar process for y-axis symmetry, but you're going to replace a negative x in your equation where there used to be x. After you simplify, if you get the same result, an equivalent equation from what you started with, then there's symmetry about the y-axis. And then the origin, this one's a little different. You have to do both. You have to replace x with negative x and y with negative y, simplify, and then if you get the same result as your original equation, then there's symmetry about the origin. Okay, so before we do an example, just so you know, some equations have no symmetry when you graph them. Some have multiple symmetries when you graph them. So we want to check all three. So test this equation for symmetry. 9x squared plus 16y squared equals 25. So we're going to do these one at a time. So the x-axis symmetry, we're replacing negative y where there was a y. So right here, we're going to plug in negative y using parentheses. And so we have negative y squared. When you square negative y, so I'll do this off to the side, you have negative y times negative y, which becomes positive y squared. So that's exactly why we get right back to the original here. So this looks exactly like the original. So this equation right here looks exactly like the original equation. Let me clear some of this up real quick. Let's get rid of that part. Okay, and then that means that there is in fact symmetry with respect to the x-axis. So this one does have symmetry across the x-axis. All right, but we don't want to stop here. We want to check for the other symmetries as well. So y-axis symmetry, we're going to replace x with negative x. And so right here, where we replaced negative x, and we're squaring it in this specific equation. So you don't always square it, it's just that this equation had an x squared. So we put parentheses, negative x. When you square it, oops, that's not squared, I already wrote it out. It becomes positive x squared. So that's why we have positive x squared right here, which is exactly the same as the original equation. This whole thing is the same. And so this one has symmetry across the y-axis also. And then our third symmetry we're going to check for is about the origin. So we're replacing negative x and negative y into our equation. So exactly where there used to be an x, we put a negative x. Exactly where there used to be y, put a negative y. Both of those squared turn positive, so positive x squared and positive y squared. And one more time, this is exactly the same as the original equation. So this particular graph had three symmetries with respect to the y-axis, x-axis, and the origin. They don't all do this. All the graphs don't always have this. This is just a really nice graph, and I'm going to show it to you. This is actually an ellipse. It looks like an oval, so that's why there's all this symmetry. Okay, so here is the graph of 9x squared plus 16y squared equals 25. So it's all kinds of symmetry on this graph. So for example, if you take the point 1, 1, notice it mirrors over here to negative 1, 1. It also mirrors down here to 1, negative 1. And then it mirrors across the origin to negative 1, negative 1. So let me just plot those 4 points so you see it. So this point 1, 1 mirrors across the y-axis to negative 1, 1. It mirrors across the x-axis to 1, negative 1. And then it mirrors through the origin, or is symmetric about the origin to negative 1, comma negative 1. Okay, so this one had a lot of symmetry, and it's because it's an ellipse. All right, let's do another one. So we're going to test this equation for symmetry. Y equals 6x squared over x squared plus 2. So x-axis testing. So the symmetry here, put a negative y where there was a y. So notice it's on the left side of the equation. And there's not much you can do to simplify this. You can, if you want, you can just divide both sides by -1. And it would just put a negative on this side and the plus sign here. So that's the only option you can really do for simplifying. And so what I want you to notice is that it's not the same as the original. So if I change that, it's up to you how you want to simplify, but it's not, what you want to get to is that it's not the same as the original. So there's no x-axis symmetry on this graph. Okay, so y-axis symmetry, put a negative x where there was an x, and notice there was x's in two places. So right here used to be x, and right here used to be x. Plug it in with a negative and parentheses, and when you square it, so same thing like our last example, when you square negative x times negative x is positive x squared. So that's why we got that here and here. And this is the same as the original. This is the exact original equation. And so this does have symmetry about the y-axis. And then our last one, origin symmetry, we're going to plug in negative x and negative y. And on this one, when you simplify, notice this is not the original. So the original didn't have a negative y. Again, you could divide by -1, and you could say, just so you know, you could say this, y equals negative 6x squared over this denominator. And that's another way just to tell that though this is not the original, that negative is making it different. And so this is no symmetry with respect to the origin. So this one had only symmetry with respect to the y-axis. So let's take a look at this one also so you see it. So here's the graph we were just testing symmetry for. And notice there is only symmetry across the y-axis. So for example, any point on the right side here gets mirrored across to points on the left side over here. And there's no symmetry about the origin. So like this point here, if I travel through the origin, it's not going to take me down, it's not going to take me down across over here. And then also there's no graph even under the x-axis, so there's no symmetry there. Okay, so a couple more examples now. This time we're going to be graphing. So graph the equation y equals x cubed by finding the intercepts and checking for symmetry. So we were working with intercepts last time, and so we're going to first find those intercepts. Remember, you let x equal 0 to find the y-intercept, and you let y equal 0 to find the x-intercept. In both cases, when I plug in a 0 for x, y is 0. When I plug in 0 for y, x is 0. So the only intercept is 0, 0. So now we're going to find any symmetry if there is some. So our first one, the x-axis symmetry, plugging in a negative y. There's nothing really I can do to simplify this when I plug in negative y other than divide by -1. So I would get y equals negative x cubed if I want to look at it that way. And all I really need to pay attention to here is that this is not the same as the original, and so there's no x-axis symmetry. And then if I want to check y-axis symmetry, I put in a negative x. Notice when you have, let me do it off to the side, negative x cubed, so negative x times itself 3 times, it's going to be negative, because a negative times a negative turns positive, but then the last negative turns it back negative. So this is negative x cubed. Okay, so I said it out loud, but let me just show you. These two become positive x squared, but when you times them by another negative, that makes the answer negative. So negative x cubed. And the point is to recognize that this is not the same as the original, and so there's no y-axis symmetry. And then the origin, if we replace negative x and negative y into our equation, this is equivalent to the original. So notice what you have. You have negative y on the left side. When you cube negative x cubed, you get negative x cubed. So the difference is when you cube this with the parentheses, it ends up still being negative, so you can remove the parentheses. And then if you just divide both sides by -1 here, or multiply by -1, same thing, you're going to get y on the left and x cubed on the right, which is the original. So there is origin symmetry on this graph. Okay, so now we're going to use the point that we found. We actually only found one intercept, and the fact that there's symmetry. Okay, so we only need to find half the points that we normally would, because we know that there's symmetry and we can use that to find the rest. So if you remember in the last video, I was telling you to choose x values, a good amount of x values, and you want to make sure you pick some negative and some positive. And so in this one, because we know there's symmetry, we actually only have to do half. So I'm only picking positive x numbers, and I'm going to use symmetry to find the other ones, which I would have had to plug in negative x's to find them. So if I plug in 0, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, and then 3 cubed is 27, 3 times 3 times 3. And so I have those 4 points. And so if we plot those 4 points, or at least the first 3, because it's kind of hard to see the last one, 0, 0, 1, 1, 2, 8, then we can use the symmetry through the origin to find the remaining points. So 0, 0 is at the origin, so that one doesn't move, but 1, 1, let me change colors so you see where I'm working. 1, 1, right here, is going to go through the origin to -1, -1. Okay, and then let's just do the last one up here. 2, 8 goes through the origin to -2, -8. And then we get this river shape, which is our graph of x cubed. Alright, let's try this example. So this one says that we're going to graph this equation, x equals y squared. And we're going to graph it by finding intercepts and checking for symmetry. And then we're also going to graph it only looking at y being positive or 0. So greater than or equal to 0. Okay, so the only intercept, just like the last one, happens to be 0, 0. Plug in 0 for x and 0 for y, and you'll find out that this is the only intercept. And then if you, we won't go through all the testing because we've been doing it for a few examples, but if you end up testing for symmetry, you'll find that there is x-axis symmetry, and then you'll find that there's no y-axis symmetry or origin symmetry. Okay, and so because of the symmetry, we only really have to find, again, like half of the points. And so if we find, this time we can choose y values, and if we only choose positive y values, that's okay, because we're going to use the symmetry to find the remaining points on the graph. So real quick side note, you can always choose to plug in numbers for x or y in any graph. On this particular graph, it is easier to choose numbers for y because something's happening to the y to make it equal x. So if it was the other way around, like the last problem where it was y equaled x cubed, it was easier to choose for x, but on this one it's easier to choose for y. So y squared is going to be x. So 2 squared is 4, 3 squared is 9, and so on. So we have those points. And so we just use the symmetry across the x-axis to map the other points. So 1, 1 mirrors to 1, -1. 4, 2 mirrors to 4, -2, and so on. And so we get this sideways parabola. Okay, so part B was if looking at the graph, only the y greater than 0 part, which is greater than or equal to 0, which is positive or 0. And so what I want to show you on this one is that this is the top half of the parabola, which is like I call this like a shooting star type shape, because you want to start to remember some of these shapes of these graphs. So this is a shooting star shape, and if you want to get this equation, you would just take the square root of both sides. So you have x equals y squared, and what I would do is I would take the square root of both sides, and I would want the principal square root, which is the positive. So normally you put a plus and minus here, but because we were told only to look at 0 or more, we're only going to keep the plus sign. And so we have square root of x equals y. And so this graph is the graph of square root of x, which is one that you actually come across pretty often. Alright, our last example. Graph the equation y equals 1 over x. Find any intercepts and symmetry. Okay, Okay, so if we check for the intercepts, plugging in x, look what happens. It ends up putting a 0 in the denominator, which this is undefined. So whenever you see this, this is always undefined, forever and ever and ever. So you cannot divide by 0, because this is saying I have one part of nothing, because fractions are a part of the whole. So this is undefined. So I tried to find my y-intercept, and I couldn't because it's undefined. Then, if we try to find the x-intercept by plugging in 0 for y, this is also not going to give us an answer, because nothing here will ever work. We'll never make this 0. And if you don't see it, if you think, oh, maybe I can solve for x, try. If you try to solve this for x, you're not going to get an answer. Watch what happens. So if I say, okay, if I try to solve this equation for x by timesing both sides by x, on the left, the x's divide out, on the right, on the x, on the left, excuse me, the x goes to 0, because 0 times x. And this is never true. 0 is never 1. So in both cases, there's no intercepts. So we tried to find them, there was none. So no intercepts. No x-intercept, no y-intercept. And you'll see why when we graph it. So it doesn't cross or touch any of the axes. Okay, so if we check for symmetry, we've done this on multiple examples, so we'll just do it real quick. Plug in a negative y. It's not the same as the original, so no x-axis symmetry. Y-axis symmetry, plug in a negative x, not the same as the original, so no y-axis symmetry. And the origin, there is symmetry, because when we plug in negative y for y and negative x for x, if you simplify by just dividing by -1 or timesing by -1, if you want to think of it as that, I'll do it off to the side just to make it clear. So this is where we're at. We just plugged in negative x and negative y. So if I simplify this by, in either way, you can divide by -1 or multiply by -1. If you simplify this, you get positive y on the left, and then the negatives divide out on the right, so 1 over x on the right, which is the original. So there is origin symmetry on this graph. And right here, our last one is the graph. So by finding some values to plug in, so we just choose, and because we had symmetry, we only need to choose half the amount of points we normally would. But if we choose some points, we can mirror them across the origin. So in this case, you do want to try some fractions, because your function does have a fraction in it. And so let's just start here in the middle. So if I plug in 1 over 1, because x gets to go in the denominator, 1 over 1 is 1. So there's my point there. And then if I plug in 2, 1 over 2 is 1/2. So 2 comma 1/2. So that one's about halfway up on the y, between 0 and 1 on the y-axis. If I plug in 10, 1 over 10 is really small, so that's like way out here. It's really low near the x-axis. And then I can just mirror those points through the origin. So 1, 1 became 1, -1. 2 comma 1/2 became -2 comma -1/2. And then I have this reciprocal function. So that's the name of this graph. Okay, notice we don't have any intercepts because it doesn't touch the x or y axis. Alright, so that was our testing for symmetry and how it helps us graph a little faster, because we can plot half the points and then use the symmetry to find the other half of the graph. Okay, thanks for watching.